So for node permutation equivariance, let's start also with a reminder that is, what is the definition of equivariance in Euclidean deep learning that applies to, for example, images. So let's look at this definition. A function f of x, so this is our network. This is the function of the mapping function in our network from the input to the output of an image x is equivariant to a transformation T of x if the output, basically, the output of the transformed image is equal to the transformation of the output of the image. Okay, so let's read this mathematically. Let's translate this, let's illustrate this mathematic formula, okay? So first, let's imagine that we have also a tree here. So this is, I'm going to put a tree here, so copy paste it. Okay, so we have a tree here. This is our image. Now we're going to apply a transformation to the image. So this is x, and we're going to translate it to the right. So we're going to get T of x here. So we apply a transformation, and then we're going to translate it here. So after we translated the image, now what we need to first, so here we have basically the transformation of image. So we need to apply f. So we're going to look at the f applied to the transformed image. So here we're going to apply f, our network, to the transformed image. And let's say our network is a segmentation network. So we want to segment this. So basically, when we do segmentation here, it means we're going to color the tree. So, and we have identified the object. So this is actually f of T of x. Okay, so this is the output, the segmentation of the transformed image. Now, what we need to look at is the transformation of the segmentation itself. So here we take the original x and we apply f. So we're going to get f of x. So right here. So this is basically f of x. Okay. And now what happens, we're going to apply a transformation, the same transformation T, okay, to f of x. So when I translate it to the right, I should exhibit the same image, which means the translation of the output of the network is the same as the output of the translated input, right? So you guys can see here we have equality, and this is the equality that we are after. It's this one. All right, so this is what it means that we have a function that is of an image x that is equivariant to particular transformation. It needs to satisfy this mathematical property, and you can see here, this is where the equality stems from. All right, now we move next. So this is the equivariance, the transformation equivariance in deep learning. And if we summarize this quickly, so here f of x is equivariant to the transformation T of x if its output changes in the same way under the transformation as the input, okay? Now, the second one is that network for per pixel image segmentation should be equivariant to transformations, which means if I translate the image, like here the tree, if I shift it or kind of rotate it, I should be able to segment it properly. So I should be able to get the segmentation of the tree even following these transformations. Okay, so now the third property is that if the image is which explains the same actually thing, so it's a rewording of this. So if the image is translated, rotated, warped, flipped, so we have a particular transformation, the network should return a segmentation that has been transformed in the same way. So the network should basically recognize that this tree has been formed and put, like a transformed output. Okay, so now the thing is, like, these properties are not very easy to stipulate in deep learning networks. So we're not gonna look at that. So I'm sure if you guys are taking a deep learning course, this should be covered in depth. So how can we actually stipulate like these nice mathematical properties, invariances and equivariances, and when training deep learning networks such as CNNs. So usually one trick is to use augmentation to rotate the images, to translate, apply multiple transformations to the original data. So the network is trained to recognize such transformations, you know, like during the learning of the mapping function. So that's one way, augmentation. So now let's look at the node permutation equivariance in GNN. So you guys can actually think about how this translates to GNNs. And here, instead of transformation equivariance, we're going to have a permutation equivariance, okay? So considering all nodes in a graph, GCN computation is permutation equivariant. And this is actually means that each layer must be equivariant, each GCN layer or GNN layer. So if we stack up layers, right, or have different building blocks, so each layer should be equivariant with respect to the permutations of node indices. And this makes sense because if you want to do labeling, if you want to do classification, if you change the index of the node, the naming of the node, it should not change its label, right? The label needs to be the same. It needs to remain, you know, the same, right? So if we permute the node indices, the node embeddings at each stage will be permuted in the same way. And basically, mathematically, this can be translated as follows. So here, if we apply the permutation to the embeddings of the previous, layer HK, right? And here we have our adjacency matrix, and these are the parameters of the transformations that we have. For example, the linear transformation that we're learning, the parameters of our network, phi k. So if we transform the input, we should also have a transformation or permutation of the embedding of the outputted embedding, which is the output of this function or this particular layer. Okay, so the output of the layer here outputs the new embedding. So if we basically permute the previous embeddings that we're going to use to do the update rule, so the message update rule, we need also to update, you know, to permute this one. Okay, so you can verify this. Actually, this is not difficult. It's the same property. It's a similar property that we have with transformations. And we can look at particular examples here. We can expand on this a bit more, okay? So for node classification and edge prediction, the output should be equivariant with respect to permutations of the node indices, because here we're doing, for example, as I said, node classifications, the label of the node itself should not change if we change the indexing of the node, and also the link itself, right? So the link between different indexing of pairs of nodes, because an edge here connects two nodes, right, with a particular indexing, okay? So as for the graph, you know, graph level tests, the final layer, it aggregates information from across the graph. So remember, guys, we use different pooling methods to transform the embeddings of all nodes on the graph. So if we have different nodes here on the graph, right? So this is our graph, for example, we have different embeddings. So we need to kind of do a transformation to get the embedding, the graph embedding HG, all right, over there. So here we have a final layer that does this aggregation across all, across the whole graphs. So the output, we say the output is invariant to the order of nodes, which means in this case, we have an invariance property. So if we aggregate, we change the indexing of the nodes. If we call this 1, 2, 3, 4, 5, or differently, so we have 1, 2, 3, 4, 5, we should always get exactly, you know, the same basically embedding. So the same output here. All right. So this would be node order permutation invariant, and the output layer in graph classification, so we have seen this formula before, so achieves the following property with respect to permutation matrix. So here, simply, it's very simple. We'll still have the same output if we permute the matrix. So we permute the final, the node matrix that we have there. So in this case, so without permutation and with permutation, we should have exactly the same output. And this is this, you know, like the mathematical translation of this. Okay. Cool. Now, for graphs, the good news, the takeaway message from this is that for graphs, it's possible to define networks that ensure equivariance and invariance properties to node permutations or node order permutations. And this is something really nice to have in graph neural networks. It makes them very easily generalizable, which means you should not preserve the same ordering because we're looking at graphs, at topologies. So regardless of where you represent your graph into a matrix or you stack your features, depending on the ordering of the nodes into the feature matrix, your network will still recognize the local topology of the node and do all the learning operations, including aggregation, transformation, regardless of this ordering. Okay, cool. So now let's have some problem solving here. So this is, you know, a simple problem. So we consider, for example, a GNN layer that outputs, you know, that applies this update rule to the embedding. So HK plus 1 is the output embedding of this graph layer that inputs the embedding of the previous layer, and HK, and then the adjacency matrix A. Now, here is D times N, so matrix containing the N node embeddings in its columns. A is N by N matrix. Beta is the bias vector. Omega is the weight matrix, transformation matrix that we want to learn for these embeddings, right? At these aggregated embeddings is the new transformation. Now, the notation here, it indicates vertical concatenation of the matrices, HK and HKA. So we concatenate them vertically. So you can actually think about it. So if we do HK, actually like this, okay? So HKA, right? And what we want to do is to show that layer is equivariant to permutations of the node order so that we have this mathematical formula, okay? So you guys, I would like you to also pause the video, take a few minutes to write this down, and let's see if you can verify this. It should be quite straightforward, I would say. So let's have a look at the solution. So it's actually very straightforward. So, you know, like here, we start with this formula, and then we simply converge to the final one. So I won't go into these details, are actually very simple. You can find the detailed solution in the PDF link below the video. All right, so this was basically the node permutation, invariance, and equivariance in GNN models. And next, we will look at the expressive power or the expressiveness of a GNN model. How can we quantify that? How can we measure the expressiveness or guarantee, I would say, more specifically, the expressiveness of GNN models?